actual theory, you're not freaked out. Because it is just classical electrical dynamics. You just say you cannot read sharp switches. You know, the Gibbs phenomenon. It's different.
What sort of being switched on?
Well, you turn on the integral. So you integrate the stress tensor against the step. So in electrodynamics, the step would be the source. So if you compute the response, you take the step and you integrate it against the retired Green's function. You get the electric field in that electric field. So it's not perfect.
Su questo video sì, sì, sì. Non dovrebbe
Mi sembra che si senta bene.
everybody's here, I think. No? So we can start again then on the lecture.
Yeah, so now I'd like to continue a bit on this theme and point out to you the connection with something called the generalized second law. I think it was mentioned yesterday by Michele Gerafici. We try to expand a bit on it. Generalized second law. So what's the second law? The second law is that the entropy must increase or cannot decrease. And now, what's the entropy? In general, it's not totally easy to define if you have non-equilibrium, but you can imagine that you can kind of define the entropy of a quantum field on some space or space-time, and you can supposedly define the entropy of the black hole itself, which is the 1/4 of the area. And the generalized second law, as was already mentioned, is the idea that one or the other can decrease or increase, but the sum of the two cannot decrease. That's in the sense that generalized second laws are very generalized because you have to take into account the black hole itself. You cannot just work just with the matter fields on the black hole space-time. So it's originally due to Bekenstein. So somewhat strangely, still to me, there is an actual argument for it, which I'm going to sketch. Though it's a bit strange. I think it's strange because, and I have no explanation for it, in that the entropy of the quantum fields involved in the second law in this formulation is the entanglement entropy. And the entanglement entropy is not really the thermodynamic entropy. It's some sort of measure of correlations of a system with its environment across a boundary, but it's not the thermodynamic entropy of the system. It's really something physically different. And so even though this is called the second law, the generalized second law, I'm not let's do something straight. But anyway, so the setting is not just with space-time. We have the future and the past horizon. Infinities. And then we have a state, so the Hartle-Hartley state. Which is a state on the entire space-time. It's a pure state on the sort of double copy or whatever you want to call it, the extended, the Kruskal extension. It's a pure state. And it's I've described its construction or outlined its construction, so you most easily constructed by, let's see, at least for free scalar field by taking the analytic continuation of the outside, where the compactification, where time is becomes the Euclidean time is a circle of whose length is the Hawking, the inverse Hawking function. So you analytically continue backward, you get this mixed state. And so we're going to call this a wedge. Calling it a wedge, because a wedge. So if you take the trace over the all these formulas with traces are formal. I just invite them for intuition. So the statement is that this is minus the temperature times the boost in K. This is the integral over plus beta H pi divided by surface gravity. So the horizon. So that's the idea here. I've already explained that. And now we have the logarithm of the modular operator, the Hawking state in the wedge, and the modular operator will be something similar. So basically the logarithm of the reduced density matrix will this is all in quotation marks, and the logarithm of this modular operator is same, but formal expressions, this modular operator is better defined, and it's more or less the same thing, except that you integrate from all the way here, whereas for the reduced density matrix, it's sort of only the half of this integral. Trying to halve this to really decouple the left and the right, which is technical. So now I'm going to look again at this sort of situation with the, what I described with the half-sided modular inclusion. I'm going to maybe consider Cauchy slice this, which intersect the future horizon in different colors. So if I look at, then I get wedge, let's say, at the causal completions of this region, WP, and so the WP defines the set of half-sided modular inclusion, and then I get an operator that one KC, as I described just before. So I'm using here K, big K for the generators of time translations. And I'm using also little k as an which is tangent to an affine parameterized. So both K and big K and little k are both tangent, both null, but one is affinely parameterized. So you know what's affinely parameterized? This is general relativity notion, yeah? And the other one is the killing field, which is not affinely parameterized, because it is actually accelerated. Yeah? Big K satisfies equation. Too many K's here, so there's, and then there's also kappa, which is gravity. Another K. The little K satisfies. A different parameterization, yeah. It's going to have both somehow. This K, and then there's plus terms from plus, and the reduced density matrix for the shifted wedge for the Hartle-Hawking space. To the minus beta. I think it's now just 2 pi. Before I had beta, or here, sorry, another K. Sorry. One K, this K is the generator of time translations. Maybe I should call it H. Anyway, it's conventional to call it K. So the difference between 2 pi here is because if I take this K has kappa plus relative to this affine parameters K. So that's why there is a difference. That's why this is not beta. Reduced density matrix from the half-sided modular inclusion. Theory. Now, I can also compute the difference between the modular operator and the Hassel-Hawkins state. Shifted wedge, and that's just have to be careful now about my signs. That's going to be integral T it's new because this T here factors out, so I'm choosing affine parameter. So an affine parameter is not unique, but it's unique up to a rescaling and a translation, and you can make this independently for every generator. So you understand what I'm talking about here, the affine parameter, and so where this surface is, this surface is where the affine parameter x plus is supposed to be T of ZA. By changing the affine parameter, you can make this T just a constant. Yeah? So this will be the multiplicative change in the affine parameter. So this is convenient. And then you have this kind of formula.
Excuse me.
Yes?
Changing the affine parameter doesn't change the surface gravity?
No. Surface gravity is defined invariantly by this formula. And the fact that K is the d by dt time shift at infinity.
Okay.
But you still have a relevant point. It's the fact that the K is really normalized relative to observers at infinity that makes the surface gravity unique. In the Windler case, the analog of K is a boost, and a boost remains a boost everywhere. Yeah, so this becomes a translation. So the K here Schwarzschild interpolates between a boost-like thing near the horizon and a translation-like thing near infinity, and that's possible because of the redshift effect. And in Minkowski, there's no such redshift effect. So this boost remains a boost, and you cannot normalize it. So in this sense, it depends then on the surface gravity is then a convention that comes in through how you measure the en route temperature with respect to what observer, how the observer is. So you just, the observer is some accelerated person, yeah, on a rocket, and the acceleration of the rocket is, how strong is your engine, yeah. So it is, but it's not a property of the space-time, but of your engine. Whereas in Schwarzschild, really, it's the property of the space-time. So this is the difference. Okay. Right. So now so you can do something, namely, you can look at the relative entropy going to call it S rel T. So that's the relative entropy between your state and the Hartle-Hawking state with respect to observers that dwell in its shifted wedge. And that's just a definition. But the point is that from monotonicity, the derivative of this, so ST is the surface. If you slide that along the stride, the shifted wedge becomes smaller, and therefore the relative entropy also becomes smaller. Yeah? That is a special case of the monotonicity where if you like, the channel here in the data processing inequality is the inclusion channel. Yeah? So the inclusion of smaller algebra into bigger algebra is also a channel. Yeah? And if you apply the data processing equality to this channel, you find that the derivative of this is always smaller. And I now claim that this gives the generalized second law. I don't know what I need to space. But is the setup at least clear, or should I elaborate? The ingredients used so far are the Hartle-Hawking state and the fact that for a shifted wedge, I arguably know what the reduced density matrix is from the half-sided modular inclusion business, which I may also encode in this more well-defined formula. Same different these formulas between the same. And I'm using the monotonicity.
Sorry.
Yeah.
So in this formula with the modular Hamiltonian, so this delta HHW, this is the Hartle-Hawking state restricted to the wedge and to the.
Yeah, that's right. So the modular operator, of course, depends on the state, in the Hartle-Hawking state, but it also depends on the algebra.
Yeah.
And here I'm using the algebra of the entire exterior, and here I'm using the algebra of the and accidentally, the ANEC in some sense can also be seen from this relationship here, because you can always show that the modular operator for a smaller region is larger. That's because its domain is smaller. I mean, that's the funny thing about modular theory. If you look at the Tomato operator, the definition is the same. It's always S of A of omega equals A star of the state. So once I presented 20 years ago, before this was fashionable, I gave a talk in, I don't remember, maybe Santa Barbara, and I explained, wrote the formula for the, for the modular operator, which is this. Omega, and then I said it's also you have to be careful. The domain of this operator is a set of vectors that you can write in this way, but the definition of the operator, if you forget about the domain, is always the same. It doesn't depend on which algebra you refer is from. So people said this cannot make any sense because it cannot be physically possible that some things depend on the domain. Yeah? So this is an extreme example where the formula is always the same for every algebra, but the domain is different and everything is in the domain. So this is expressed also here. Here the domain is smaller, and therefore the operator in this sense is bigger. And that gives a sign to this expression. This is the digression. So let's see how we go from here to the generalized second law. So again, we have S real 0. And what's S rel? I'm going to write it with traces. And so it's the reduced density matrix of the stage. Let's call it T. So let's define what is T is a density matrix. State under consideration. T is the reduced density matrix of the Hawking state. And this is the formal formula for the relative entropy. And I also explained that this would be given by e to the minus 2 pi t, and kt would be given by now, you can therefore take the logarithm formally of this. And this will be in terms plus, and you can take formally the logarithm of this. So log of minus 2 pi. T. So you can rewrite this first term, and I already said that last lecture. The first looks basically like the von Neumann entropy, just with the minus. Minus von Neumann entropy, usually in this business is just called the entanglement entropy. T, or this state here. And minus this gives 2 pi times the expectation value of kt. You can formally write it like this, and this, you do it like this. You can. It's kind of easier to take the derivative. So let's now take the derivative. So here I'm just going to take in t. So here the derivative, I'm just going to write the derivative and not do anything. And on the second term, I'm going to take a derivative. So the t appears down here in the integration domain, and it appears in the integrand, so I have to differentiate both. However, if I differentiating the integration domain. So this means that the integral is from t to infinity. That means that the integrand is evaluated at the lower boundary, but due to this factor, it vanishes. So only contribution is when I differentiate t under the integral. That gives me minus integral of 2 pi mu, and then plus yeah, I'll divide it like this. So this d as nu like this, and d as nu I'm going to write as dx plus times dA times nu, volume element. Written and then minus 2 pi integral from t to infinity dx plus, and then integral over the sphere, so dA theta k k. So now you see maybe where this is going. I'm now going to postulate the semi-classical Einstein equation. Which states that phi is a mu nu, phi is going to be g mu, and the kk component will then give me here the Ricci tensor divided by appropriate powers of pi. So therefore, the k component is 1 over 4 Newton, and times the Ricci tensor dotted twice into k. And the Ricci tensor can be expressed with my Ricciardori equation. So what was the Ricciardori equation? So my affine coordinate now is x plus. This way, affine coordinate. So the Ricciardori equation is that this is the expansion in the plus direction, derivative is minus expansion in the direction, and then the shear squared in this direction, and then minus Ricci plus plus. So k. can think then that you can make this substitution here. First, replace the 2 pi times the expected stress tensor by 1/4 G Newton times the plus Ricci tensor. And then, after you make that, you replace the plus Ricci tensor solving this equation in terms of the expansions and shears. So this really all looks very promising and nice. And so you doing this trivial algebraic step allow me to r plus then minus shear and then minus Jim. So this is quite nice because you're going to afterwards integrate in x plus, so it's nice to have a derivative, so the integral is easy. These terms are not particularly easy to integrate, but they have a sign. I would, so remember what we're trying here to calculate is this, and this was the relative entropy T, and this had a sign. So if we minus r plus plus, either you say it has a sign, or you say that's a kind of a dirty way to do it. You say this, after all, is a quantum correction, so there's an h bar here, or a G Newton, if you like, and this is a semi-classical approximation. So if G Newton is very large, nobody on Earth is going to trust that equation anyway. So G Newton is very small, so the expansion caused by this quantum stress energy tensor is going to be very small. I mean, the expansion of the generator is in the background, Schwarzschild is 0. So the expansion caused by the quantum effect is very small, so the square, and likewise the shear, the square is even smaller. And so you can either say that it has a sign or you neglect it. So I would prefer to neglect it. Why? Because also nobody really believes that Einstein gravity is going to be the end of the story, but it's just an effective theory, and there will be all these other terms, higher curvature terms from higher effective theory corrections, or from alpha prime correction in string theory, whatever. So you're on the safer side to say that this is just negligible. And therefore you then just replace this to minus 2 pi by minus g minus r minus here. So you can replace this thing by 1/4 Newton x plus, and then dA d plus. And remember, maybe in my previous lecture, I was drawing this picture, and I'm going to draw it again of some expanding geodesics. They start out with some parallel, and there's some area element dA, and then after a while there is a new area element dA later, and the expansion, of course, is telling you how different is this new area element from the old area element. So intuitively what expanding means. And therefore, if you integrate that up, you learn that that this kind of expression, so you learn that this is minus the entanglement y of E, and then you learn that this is minus, the derivative is it's the lower side here, so D is the upper minus lower, yeah. So you really keep the lower, and so this would be the A. As you see, this is has the form of the generalized second law, because everything was supposed to be less than 0, so therefore entanglement entropy plus the area over 4 prime is greater than or equal to 0. This is the generalized second law, in the sense that the combination of an entanglement entropy plus 1/4 area, and that changes it as a change as a sign. Okay, that in a nutshell is the generalized second law. Its assumptions here are the semi-classical Einstein equations, and the rest is a very nice interplay between algebraic quantum field theory, quantum information, and semi-classical physics. Now, I think I was going to say something about the QNAC, which is a kind of interesting variation on this, but I think that for 15 minutes will not be really enough for that, and I'm just going to skip it. I think that's a nice way to end my lectures. In any way, you can read up on it in my lecture notes, of which what I've presented is a certain part, and some parts go beyond it. You can read up in many other places too. Thank you.
Many thanks to Stefan for his lecture. Now, any question?
I think I just missed it, but why did you not get a contribution from the other parts of the interval?
I would have gotten one, but I'm saying that eventually this is going to settle down, and the expansion at late times is going to be negligible. So I just by hand say that there isn't a contribution. That's not very suspicious, I would say. But that's a good question.
Any other question?
You can still ask me personally.
Where can one find your lecture notes?
They're on the archive.
Ah, okay.
So I gave the number. I can, if you want, I can write down the archive number. Yeah, we can go for the break now.
Okay, thanks again. So we resume at 2:30.